Hello, and welcome to Lab 1, Latitude, Longitude, and Location. The spherical coordinate system of latitude and longitude. Successful navigation depends on the ability to determine not only one's current location, but also one's desired destination. The system used to define one's location is the spherical coordinate system of latitude and longitude. The spherical coordinate system is based on the spinning spherical Earth and consists of two basic features. The rotational axis, which is defined by north and south geographic poles, and the equatorial plane, which is perpendicular to the rotational axis. These planes define the basis to the spherical coordinate system and the development of lines of latitude and longitude. Lines of latitude. Latitude lines are imaginary lines that run horizontally or east-west, and they are perpendicular to the Earth's rotational axis. They measure from 0 degrees north-south latitude to 90 degrees north and 90 degrees south at the geographic poles respectively. The equator is defined as 0 degrees north-south. It is the primary line of latitude. It's measured equally distant from both poles, and it divides the Earth into the northern and southern hemispheres. It is important to understand that while lines of latitude run horizontally or east-west, they determine one's position north or south of the equator. Additionally, latitudes closer to the equator are low latitudes, and lines of latitude closer to the poles are high latitudes. Lines of latitudes are called parallels. This is because the spacing between lines is constant. Thus, latitude lines never intersect. Additionally, notice that their circumference progressively decreases from a maximum circumference at the equator to just single points at the poles. Lines of longitude. Longitude lines are imaginary lines that run vertically or north-south. Unlike lines of latitude, longitude lines are not parallel and they converge at the north and south poles. They measure from 0 degrees east-west at the prime meridian to 180 degrees east-west. The prime meridian is defined as 0 degrees east-west. It's the primary line of longitude, and it's defined through an engraved benchmark in Greenwich, England. The prime meridian divides the Earth into the eastern and western hemispheres. 180 degrees east-west of the line of longitude, directly opposite of the prime meridian, is called the international dateline. It's important to understand that while lines of longitude run vertically or north-south, they're used to determine one's position either east or west of the prime meridian. Longitude lines are called meridians, derived from the Latin term meaning noon, because when the sun reaches its highest point in the local sky, or local noon, it occurs simultaneously from pole to pole along any given longitude. Additionally, it's important to note that while all lines of longitude are equal circumference, meaning they all split the globe into equal halves, the distance between lines of longitude progressively decreases from a maximum at the equator to 0 at each geographic pole. Later in this lab, you will learn why this is important when measuring distances between locations. Reporting location in latitude and longitude. Although lines of latitude and longitude are drawn in degrees, any location can be reported more precisely by dividing each degree into arc minutes and arc seconds. For example, for the 360-degree spherical Earth, each degree can be divided into 60 arc minutes, or 1 degree equals 60 minutes. And each arc minute can be divided into 60 arc seconds, or 1 minute equals 60 seconds. These are important unit conversions and can be best thought of as ratios. Here we see the unit conversions written as ratios. For example, a 1 degree per 60 arc minutes is equivalent to 60 arc minutes per 1 degree. Likewise, 1 arc minute per 60 seconds is equivalent to 60 arc seconds per 1 minute. Next, we will take a look at how properly reporting a position is done using degree, minute, seconds format. The following example is a general overview of how you report location later in your lab. For example, let's take a look at the position of San Diego State University. San Diego State University is located at 32 degrees north because we can see that it's above the equator, and 117 degrees west, again west, because we can see that it's west of the prime meridian. Finally, a more precise position may be reported by using degrees, minute, seconds. Here's an example of the proper format. Latitude, latitudes reported first at 32 degrees, 46 minutes, 33.56 seconds north, followed by longitude at 117 degrees, 4 minutes, 16.51 seconds west. You'll be working with degree, minute, seconds format later in your lab, but first, there are a few more key principles that we want to introduce. Great circles and the Earth's surface. Geometry teaches that a perfect circle is produced on the surface of a sphere when a plane intersects the sphere. If the plane intersects the exact center of the sphere, then a great circle is produced on its surface, which essentially divides a sphere in half. In contrast, if a plane does not intersect the exact center of a sphere, then a small circle is produced on its surface. Small circles can range from just slightly smaller than a great circle, as seen near the equator, to just a single point at the poles. Based on these definitions, all longitude lines are great circles, as well as the equator is a great circle. All latitude lines are small circles, with the exception of the equator, whose plane intersects the exact center of the Earth. The nautical mile. Next, we will discuss the nautical mile, an essential unit of measure in the spherical coordinate system. The nautical mile is defined as 1 arc minute of distance in latitude along a great circle at sea level over the Earth's surface. Thus, 1 arc minute equals 1/60th of 1 degree around a given 360-degree circle. This creates the important 1-to-1 ratio of 1 arc minute equals 1 nautical mile. Furthermore, based on the relationship between degrees, minutes, and seconds, the following conversions are true wherever the 1-to-1 ratio exists. Where 1 degrees equals 60 minutes, which equals 3,600 seconds, 1 degree equals 60 nautical miles, 1 second equals 0.167 nautical miles, or 1/60th, and 1 nautical mile equals 1.15 statute, or standard miles, which equals 1.85 kilometers. Next, we will discuss this 1-to-1 ratio in more detail and how it relates differently to lines of latitude compared to lines of longitude. Nautical miles. Measuring distance between latitudes. Let's begin by looking at how the 1 arc minute to 1 nautical mile ratio relates to measuring vertically between latitudes. To measure distances north-south, measurements occur along lines of longitude. 1 arc minute along any line of longitude will equal 1 nautical mile in latitude. This is because lines of latitude are parallels and are equally spaced. Lines of longitude are great circles, so the measurements along any line of longitude traveling north-south will equal 1 arc minute, or 1 arc minute equals 1 nautical mile, again because lines of latitude are equally spaced. Measuring distances in longitude. When we measure the distance horizontally, however, we're measuring between longitudes. East-west measurements occur along lines of latitude. Thus, the ratio of 1 arc minute equals 1 nautical mile will only be valid along the equator. This is because the equator is the only line of latitude that is a great circle. Distances between longitudes decrease in latitudes higher or lower than the equator, north-south. And again, this is because lines of longitude converge to a single point at the poles. Because lines of longitude converge, the 1 arc minute to 1 nautical mile ratio no longer applies as the distances between lines decrease. Thus, a table is used to provide decreasing ratios per latitude. Later in your lab assignment, we'll practice using this conversion table. Spherical coordinates and time. Coordinates and longitude are based on time. The Earth rotates eastwardly on its axis at a rate of 360 degrees of longitude every 24 hours, or 15 degrees per hour. Thus, time zones on Earth, as well as location, are determined by the speed of rotation. Thus, when people experience local noon, who are living along the prime meridian or at 0 degrees longitude, people living along the international date line or 180 degrees longitude are experiencing local midnight. The UTC time constant. To avoid global confusion due to local time differences, a global time standard known as the Universal Coordinated Time, UTC, establishes current time at noon at the prime meridian. To determine one's local time from UTC time, 1 hour is added to UTC time for every 15 degrees of longitude to the east, and 1 hour is subtracted from UTC time for every 15 degrees of longitude to the west. Additionally, to avoid confusion of morning and evening hours, time is reported in a 24-hour format. For example, 0900 equals 9 a.m. and 1600 equals 4 p.m. San Diego local time. Let's determine the local time of San Diego State University. We can do this using one of two methods. One, if you have a time zone map, then you can merely count the time zones. When we start from UTC time, there are 8 or -8 time zones to San Diego. So if UTC time is 11 hours, then San Diego local time is 0300 in the morning, a difference of 8 time zones to the west. A second method is to use the known rate of rotation of the Earth at 15 degrees per hour. Given the longitude of San Diego at 117 degrees west, multiply to determine the time zones. This will equal approximately 8 time zones. Thus, 8 hours must be removed from UTC time. Here it's important to note that realistically, many time zone boundaries do not follow lines of longitude. This is due to various geographic and geopolitical purposes. Later in your lab, you'll revisit these relationships between time and the Earth's rotation to determine one's position in longitude. Navigation, the sextant. A sextant is a measuring device used to locate one's position north or south of the equator. Used at night, it measures the angle between the horizon and a circumpolar star. In the northern hemisphere, Polaris, or the North Star, is aligned directly above the North Pole. In the southern hemisphere, the Southern Cross, or the Southern Star, is aligned above the South Pole. The angle between the local horizon and Polaris, for example, will be equal to one's local latitude. It's important to note that the sextant only measures one's position in latitude within either the north or southern hemispheres. It does not measure longitude, and it cannot tell whether one's position is within the eastern or western hemispheres. To do that, we use a chronometer. The chronometer is a precision timekeeping device used to determine one's longitude, measured at local noon, relative to UTC time. For example, before leaving port, a ship's chronometer is set to the home time at the home longitude. One's current longitude is calculated from the time difference between your current time, taken at local noon, and the chronometer's UTC time. Because the Earth rotates eastward at a rate of 15 degrees of longitude per hour, we can use this ratio to calculate local longitude. For example, a 0600 UTC chronometer reading taken during local noon would indicate a local longitude of 90 degrees east. Later in your lab assignment, we will use the chronometer readings to determine position and longitude and to determine if you're located in the eastern or western hemispheres. Finally, we will discuss unit conversion, or what's known as dimensional analysis. This involves the mathematical conversion of units to their equivalents. For example, convert the quantity of 14 meters per second to statute or standard miles per hour. To begin, you'll need to know the correct unit ratios to convert your units. Throughout this course, your lab TA will provide all necessary unit conversions. In this example, we use the following unit conversions. Start with 14 meters per second. Use the appropriate unit conversions to convert the units to miles per hour. Based on cross-cancel multiplication, you can change meters to kilometers, then kilometers to statute miles, seconds to minutes, minutes to hours. Then by dividing the products of the numerators and the denominators, we can calculate that 14 meters per second is the equivalent of 31.5 miles per hour. Later, you will watch a more detailed video to help you with your lab assignment. It's now time to begin your lab assignment. To assist you, a separate video tutorial is provided for each section. Begin with video 2, Dimensional Analysis and Calculations. Please address your questions to your lab TA.